Hi everyone, welcome to today's webinar, which is brought to you by us here at Simply Rhino and Intact Solutions. I can see some people are still logging on, so welcome to those that are just joining us, and I hope everyone can hear and see everything okay. Please let us know if you can't. You can send us a message in the chat window. So in the meantime, I'm Steph from Simply Rhino, and I'll be introducing Michael Freytag from Intact Solutions, who'll be making today's presentation, in which we'll be looking at Scan&Solve Pro. So Scan&Solve Pro allows the structural performance of shapes to be predicted without building physical prototypes. Strengths and weaknesses of designs are easily determined using different materials and loading conditions. Scan&Solve Pro is a plugin that integrates with Rhino, so simulation is easy at any stage of the design process. So before we move on to the presentation, a couple of quick webinar housekeeping notes. If you've got any questions, then please type them in using the question panel and send them over to us. We'll answer all these following the main presentation. We'll do a little Q&A at the end. And also please note that we're recording the webinar, so we'll be able to share it with you afterwards. So that's all for me. I'm going to hand over to Michael now for the presentation. Over to you, Michael.
All right. Okay. Thank you, Stephanie, and I thank Simply Rhino for hosting this today. It's a wonderful opportunity for us to show off Scan&Solve Pro and connect to our community. So thanks again. So today I'm going to be talking about Scan&Solve Pro for Rhino, which is our latest product in the Scan&Solve family. It's a simulation product that builds on the success of Scan&Solve 2014. So I'm not sure how many of you are familiar with Scan&Solve 2014 or the Scan&Solve product, but I'll give some overview on why do we want to do simulation, some of the motivation behind it, and also show some demos of Scan&Solve Pro in action. So why simulate? Simulation allows us to predict the product performance early in the early stages of design, in the stages where the product cost is largely determined. They say that up to 70 to 80% of product cost is determined at the conceptual design stage. So if we can make decisions on the geometry and the shapes that we're using, as well as the materials that we choose early in the stages of design, when we have the most control over cost, it's always a good thing. Simulation also allows us to identify and avoid design mistakes early in the design process, when the repairs of the mistakes are easy to make, rather than later on in the design process, where you have to redo you might have to redo an entire design. So here's some examples from early in Scan&Solve development. These are examples from Ian Boyd, who was a chair designer or worked for a chair design company. The example on the right is a failure, actually, of a piece of equipment in their facility. He was able to use Scan&Solve to design a replacement component using different materials, but functionally equivalent. And on the left, there's an example of a chair design where he was able to identify the locations of some failures and identify a way to fix the design deficiencies and reduce failures in service. So another reason to use simulation is we can evaluate geometries for performance, so we can predict the stiffness stresses and the material utilization. And we can also use the information from the simulation process to guide geometry modifications. So you can identify where you have high stresses and increase material thickness, or identify regions where you have low stresses where you can remove material. Simulation also allows us to compare and select alternative designs. The example below in the picture shows an example that I pulled off of GrabCAD, where there's a variety of choices that we can make in this design, and we can, depending on those design choices, we can get different factors of safety, and we can determine this stuff early in the design process without building a physical prototype, installing it on a ship. In this case, this is a winch frame, so we can identify these things early and get a good design without having to go back and do rework. So why Scan&Solve Pro? So Scan&Solve Pro is the evolution of Scan&Solve 2014. It still has all of the capabilities. So we have the FEA without meshing. So we have simulation at the touch of a button. So there's no pre-processing, no meshing, no defeaturing, none of the expensive and time-consuming steps that prevent simulation from being applied to a design. With Scan&Solve Pro, we can simulate bonded assemblies. Previously, in order to simulate an assembly of components in Rhino with Scan&Solve 2014, we would have to use the union operator, the Boolean union, to combine a bunch of different components into a single component that had a single material. If you're familiar with Rhino, unions can sometimes be a problem. You'll have and that's something we can easily avoid with Scan&Solve Pro. Another feature of Scan&Solve Pro is the ability to mix different materials. So you can have different materials with different applied to different components, and you can try different configurations of components very easily. So you can move components around, try different positions of them, add, subtract, and do simulation with these different configurations. And you can, with Scan&Solve Pro, we also can simulate with complex materials, including wood and bonded composites. Previously, we were limited to only isotropic materials like plastics and metals. And like earlier versions of Scan&Solve, it's very easy to use. It's integrated directly into Rhino, so simulation is a simple touch of a button, a few keystrokes, and you can get results. So I'm going to do a quick demo of a timber frame structure using Scan&Solve Pro in Rhino. So let's pull up a timber frame. So on the screen, we've got a timber frame structure. This is about, I guess it's about 5 meters by 5 meters by 5 meters. The top part is made out of wood, and we've got concrete bases to the bottoms of these columns. So to run Scan&Solve Pro, we type SNS Pro at the command line, and we're presented with a scenario selector. On the very first run of Scan&Solve Pro on a Rhino document, you will not be presented with this. You'll be taken directly to the next page or next dialog box. So what we want to do here is we want to add a simulation or add a scenario, and we'll hit OK. So now we're editing a new scenario. It's very simple to set up a simulation. We start at the top and work our way down to the bottom. So starting at the top, we want to choose a meaningful name for our scenario up here. Rhino. And now we want to add components. So every simulation scenario is comprised of a set of components to which materials are applied to associated with each component. A component is basically a solid in Rhino, which can be an extrusion, a closed valid poly surface, or a closed valid mesh. So what we want to do is add some components. We will click the Add button. We will select all of the timber parts of our timber frame, and we're immediately presented with the material selector dialog. And this is made of wood, so we choose the wood tab. We can choose a variety of woods that are included with the distribution, and we're going to choose. We'll choose Douglas fir. Now with wood, we have to choose a wood grain orientation. So we've got a variety of options down here. I'm not going to get into the advanced ones like specify and guide. We'll reserve that for the next webinar. But for the purposes of this webinar, I'm going to choose rift sawn. So wood grain wood is cut out of a tree in different orientations, and rift sawn is a particular type of cut. If you're familiar with timber construction or cabinet making, these are meaningful to you. We also have documentation that you can see if you want to see it. So I'm going to choose rift sawn. And what Scan&Solve Pro will do is identify the principal moments of these geometries and apply the wood grain in such a way that the long direction is aligned with the long dimension of the geometry. In some cases, the shape is ambiguous about which orientation is which. So in that case, the Scan&Solve Pro will highlight these items, these components, and we will have to select the orientation ourselves. So to do this, we're going to select the origin of the grain coordinate system and then the long direction. So we'll select the long direction this way, and then the radial grain direction like this. And then it's going to cycle through all of the ones that are ambiguous to it. So I'll just repeat this process. So we've specified wood for all of the timber. Now we want to add some components at the bottom, which are the foundation supports. Oops. Click Add. We add this, select this foundation supports, and we're going to make these out of a fairly high strength concrete. If I can find it, fairly high strength, choose Apply. Now, in order to do a simulation, we need to restrain this somewhere. In the case of this structure, we're going to restrain the bottoms of these foundations. So now those are fixed in all directions. I could apply loads, but I'm just going to choose gravity for now. And I'll specify resolution around 30,000. Now, because we've got a variety of solvers we can use, I'm going to use the fastest solver. Typically, by default, we'll choose the SNS solver, which is an iterative solver. So it's a slower solver, but it doesn't use a lot of memory. The DSS solver is a much faster solver, but it can be unpredictable in terms of the amount of memory it takes. So I know this is okay at 30,000, so I'm going to choose it. And we click Go. So what it's doing right now is Scan&Solve is going through and adding all the contributions of these different components into a large mathematical system of equations, and it will solve these systems of equations to figure out how this shape is going to deflect under the gravitational load. It takes about a minute for this shape, so just bear with me for a few more seconds. So our simulation is complete. It took 1 minute 38 seconds, as we can see right here, which isn't too bad, and setup was very easy, as you saw. For those that are familiar with Scan&Solve 2014, all of these controls on the View tab should look very familiar. The orientation is, the layout is slightly different. We're going top to bottom instead of left to right. At the top, we've got the solution components that we can select from. So right now, we're showing the total displacement. We're seeing the maximum displacement of 3 thousandths of an inch at probably around the center here. There's a variety of solution components available. For those that are interested in the stresses, we can choose the von Mises stress, and we can see the stress distribution within the shape. The architects are interested a lot of times in the principal tension and compression. So that's a solution component that's available. And a lot of times to help display this, it helps to center the display, the solution range, and also to choose a different legend color scale so that it's a sort of a binary color. In this case, the tensile, the regions that are in tension are in red, and the regions that are in compression are in blue. We can use the deflection slider to get a visual depiction of a magnified displacement. So if you were to take the initial displacement and magnify it, so in this case it's 6,000 times it's what it actually happens, this is the shape you would get. Next, we can use the marking tools. We can identify the minimum. It inserts a leader where the minimum of the currently displayed solution quantity is. We can use the point tool to choose points on the geometry where we want the solution value. And we can also use the max tool, or the max marker, to identify the location of the maximum of the currently displayed solution component. We can also clear those marks. I'm not going to turn on section display because with this many components, it's a little bit slow and it's not particularly interesting. But we can enable a section display and slide that to and fro in the geometry. You've already seen that I can also select different legends, different legend color scales. This is pretty standard stuff. And we can also do the output in terms of we can output the geometry as we can bake the deformed shape as a textured geometry object in Rhino, or we can write it out to an output file in either as a VRML file or STL/PLY. And of course, there's always the report button, so we can generate a web-ready report by clicking the report button, and it will go. Scan&Solve will go through and generate a report that will then be pulled up in the default web browser. In the report, we've got the assembly geometry, we've got the material description, summary of the materials that are being used, and then we've got a list of the components that make up this assembly, and there's a lot of them. So that's the basic setup and simulation process for an architectural type example. Now, a lot of times it's interesting to try to change the material that we're using, and that's very easy to do. We can select all of the components that make up the timber part of our timber frame. I think this is all of them. And we choose the edit button, and we can choose a different wood. Right now it's set for Douglas fir. We can choose bald cypress. We can choose any one of these and hit apply. It will save the grain orientation for a subsequent run. So right now I can hit go and it will solve again using the new material selection. I'm going to stop it here because it's going to take a little bit of time. So I'm going to hit done, but I will go back to one of the ones that is already solved and show how we can also apply different types of loads. Before we just had gravity, we can also apply for example, a wind load by choosing, I'm going to delete this one and add a wind load. So now we select the faces that we want to apply, to which we want to apply the wind load. I don't know why it's doing that. So it was already set up, the previous one was set up for a scalar force of 5,000 pounds, but so we're going to say a 5,000 pound wind load. Well, that's not going to work. It's going to be 5,000. 5,000. So this is approximately 20 pounds per square foot, I think. Oh, I should go back there. There's a variety of loads as with Scan&Solve. The same set of loads can be applied, so we can apply a vector force, which is a directional force, We can also specify a vector force by choosing a direction and a magnitude. Scalar force is turned into a pressure. A pressure is just a pressure, which is applied over the faces. Then we can also insert a pressure expression, so which put in a mathematical function of x, y, and z. Hydrostatic for water type loads, or like a tank load, or inside of or the outside surface of a hull of a boat, or even torque load for maybe the end of a shaft or something like that. So that's a variety of loads we can set up. I'm going to cancel out of this and run it again, just so we don't have to sit through and wait for the solving process. So here we can see what happens with that applied wind load. We see a lot of shear of the shape across because of that load being applied to one side. So that's an architectural example. We also have an example here of a winch frame. So a winch frame looks, this is a part of a component. A lot of times on ships they have these winches. So this is an example of a particular design for a winch that I borrowed from GrabCAD. So this example allows us to show how you can combine different designs or different components into a single design. So this scenario has all of the parts. So actually, let me do this one. So this one has no ribs. So this design has this simulation has a vector load applied of 300,000 newtons in the x direction and 100,000 in the z. This simulation includes the basic frame, but it does not include these filler pieces or the green ribs. So we can see what the results look like for this one. And we choose to show the von Mises stress. And we can see how it deflects under the load we had. As you can see, the ribs and the filler pieces are not included in this simulation. But we can also, what we can do is we can look at the danger level for this particular configuration. And we can see that the peak is 0.63. So this is a factor safety of 1 over that, which is about 1.6. But we can easily compare that to a model that contains all of the parts. So instead of having cutouts in the side frames, we can pretend that they are not cut out by actually filling them in with the same material. And we can see what the results look like with this. The same loading is applied, the same material properties. We just have more components added to this whole thing. So let's view the results. And we can see by looking at the danger level that the factor safety is now about 2.5, which is 1 over the 0.4 for the danger level. So it's very easy to mix components, mix materials, add components, delete components from the interface, and I think we try to make it as easy to use as is possible. So I recommend that you try Scan&Solve for yourself. You can download the Scan&Solve Pro from our website from this link, which will take you to our web page where you can sign up. I will send you. I apologize for the train. So you can put in your name, you can download it. You can also visit the documentation to see if you have any questions. We also have a YouTube channel with videos. I apologize for the train. It's going to be done passing shortly. We also have the forums. If you are interested in participating in the community or want to ask questions, you can go do that there. Ask for support from some of your compadres, or ask us for support via email. You can buy Scan and Solve through Simply Rhino, or you can come to us. And with that, I conclude my presentation, and I appreciate your attention, and thank you for attending today. If there's any questions, please put them into the question box, and I will try to answer them.
Hi, Michael. It's Steph back here now. That's a great train in the background.
Thank you.
That's great. They're normally very long, aren't they? They're very long and very loud. So yeah,
right.
We have some questions.
Okay.
So Miguel has asked a couple of questions. The first one is, I'll just read the question out. I would like to know if it is possible to see the tensions and forces in a piece, but without knowing the material, just knowing the form. That's the question. Hope that makes sense.
Without knowing the material, I don't. With Scan and Solve, it is what we do is a simulation which requires the material to be specified. But for most, or for typical materials, for typical isotropic materials like metal, plastics, the material selection shouldn't make a difference about shouldn't affect the form, what am I talking about? You should be able to simulate with any material to figure out how it's going to deform under a given loading if you're using a material like metal or plastic. But in order to do that, we do need to specify material.
Okay. All right, great.
I hope that answers the question. If not,
yeah, I think so. Miguel, let us know if that doesn't. Here's the second question, which is how to configure the loads. So.
Okay. So yeah, I didn't really show that. So for example, this one, what I can do is I'll just show how to add another load. Excuse me. What I'll do is add a load to say the inside surfaces of these, so as if the winch drum is being pulled down. The process is we select the faces to receive the load, and once we've done that, we click enter, and we can choose any one of these forces or one of these load types. So I'll choose a vector force in this case, we'll say this is the weight of the drum. So there's no force in the X direction, no force in the Y, and there's maybe 20,000 newtons of force in the Z direction. So this is a force downward. We could also do it by a scalar force, by choosing the direction within the interface using the directional force. So in this example, I would just choose this direction. I'll turn off ortho, so we can do this. And now we choose a magnitude of, like, say, 20,000 or 25,000 newtons for the weight of this of a drum, say, installed on this axis. And that is basically applied, and we see the annotation inside the display. If there's a specific question, a type of load that he's interested in, I can do that. But this is a very basic overview. There's a lot of detail that we can
go
into.
Sure, of course. Yeah, that's great. We just had a nice thank you there from Miguel. Another question for you, please, Michael. This one's from, I hope I'm pronouncing this correct, from Shahay. And the question is, he says, hi, how do you determine the type of connections if, for example, the wood is assembled by bolt, nail, or glue?
So right now, the Scan&Solve Pro uses the notion of a connection is not really there. We're not at that position yet. What we have is if the solids are in contact or very close proximity, then they are considered as glued. That's the simplest type of sort of connection that can be done. In the future, we'll probably be implementing other types, but for now, it's basically a glued or a bonded or a welded is sort of the type of connection that is available. So there is no choice about bolted or other things.
Okay.
That's not to say you can't mix materials. So if you wanted to, say, put a steel plate on the side of a wood beam, that's doable. It will just be treated as if the steel is glued to the wood.
Okay, I understand. I hope that answers the question, Shay. We have another question here. This one's from Vladimir, and the question is, how does the meshing work? What if you have a stress concentration? Would it automatically refine the mesh in such location?
There is no step for mesh refinement. We use a uniform grid, which you can actually see by turning on the grid. So there's one resolution slider that controls the resolution globally. There is no local refinement as of now. That is on our radar, and we are working on hierarchical grids or elements, so we can increase the resolution to take into account stress concentrations, or if the user would be interested. We're just not there yet.
Okay, cool. And one last question. That's a thanks in here. And one last question, please. This one's from James. Oh, sorry about the phone. The question is, how do I control whether parts are bonded or not?
Right now, in this current version, the bonding is determined by the size of the grid spacing. So if they're in proximity, they're basically bonded. So if you have if these individual cubes cross a boundary or cross an interface, then the objects that are included in that are considered bonded there. This is very related to the earlier question about how to handle different connections. So the only connections we have right now are bonded contact.
Sure, brilliant. Okay, that's it. I think we've answered all the questions that we have had so far. So if anyone's got any other questions following this, then of course drop us a line and we will ask Michael to answer them for you. So Michael, thank you very much, and thanks to you and your team in Tax Solutions. To everyone, we have another webinar with Michael in 2 weeks' time, and that's on Wednesday the 31st of May at the same time, which is 3 p.m. here in the UK. I'll leave it for you guys to work out where it is with you, because I know we've got a worldwide audience here. We'll send a registration link to that webinar in the follow-up to today one to all the attendees. So thank you to everybody for joining us, mostly to you, Michael. Thank you. That was really great.
Okay, thank you.
Hope to see everyone again soon.